The observable universe is home to truly astonishing large-scale structures that represent the breadth and depth of cosmic architecture. Among these giants are galaxy superclusters, large groups of galaxies that are gravitationally bound together. One of the most prominent superclusters is the Laniakea supercluster, which serves as our cosmic neighborhood. It contains approximately 100,000 galaxies and spans over 150 million light-years, representing the mind-boggling scale involved in our universe. In addition to superclusters, there are even larger formations known as cosmic filaments. These filaments consist of galaxies and dark matter, weaving complex patterns into the large-scale structure of the universe. The Sloan Great Wall is an important example of a cosmic filament, more than 100 million light-years long. Such large structures are interconnected to form a vast web architecture with empty spaces between them. This suggests that galaxies are not evenly distributed throughout the universe, but rather they form a complex region under the influence of gravity and dark matter. Even more impressive are the largest structures ever discovered, such as the Great Wall of Hercules Corona Borealis. This massive supercluster measures about 10 billion light-years across and is considered the most well-known structure in the observable universe. Its discovery complicates our understanding of cosmic evolution because it raises questions about how such large regions come together and what forces govern them. These massive structures provide important insights not only into the vast scale of space, but also into the fundamental processes that shape the universe over billions of years. As scientists continue to study them, they learn more about the basic fabric of matter, energy, and nature. The pursuit of knowledge about these great clusters piques our interest and our desire to understand our place in this grand cosmic scheme. Galaxy filaments and cosmic networks are the result of gravitational interactions and the complex dynamics of dark matter in the universe. These structures appeared in the early stages of cosmic evolution after the Big Bang. As the universe cooled, matter began to clump together under the influence of gravity. Dark matter plays a key role in this process. It does not interact with light, making it invisible, but its gravitational pull has a significant effect on the distribution of galaxies. Over billions of years, regions with a slightly higher density of core matter began to attract more matter, forming the seeds of galaxies and clusters. As these local gravity wells deepened, they attracted more and more material from their surroundings. This created filaments, which are long structures that look like spaceships. These filaments connect large clusters of galaxies and form the web structure that fills the universe. As the universe continues to expand, the dynamics of matter evolves. Galaxies within the filaments are attracted to each other, eventually forming clusters at their intersections. This gravitational hierarchy is surrounded by high-density large voids that contain relatively few galaxies. The interplay of filaments provides the foundation upon which the universe is structured, displaying a beautifully orchestrated spatial arrangement. Computer simulations and observational data from telescopes are further enhancing our understanding of this phenomenon. These simulations show how dark matter affects the evolution of cosmic structure. Large-scale surveys, such as the Sloan Digital Sky Survey, allow astronomers to detect and map these large filaments, confirming theoretical models. Together, they reveal the dynamic processes that create the elegant cosmic web that spans our universe. Cosmic voids are the vast, empty spaces between galaxies and galaxy clusters that represent some of the larger structures in the universe. These voids can be tens to hundreds of millions of light-years across and are characterized by a lack of matter compared to denser regions. Although they appear to be devoid of galaxies, a closer inspection reveals that they are not entirely empty. They often contain faint galaxies, dark matter, and diffuse gas, albeit in much lower concentrations than their denser counterparts. The existence of these cosmic voids provides insight into the overall structure of the universe. The proliferation of voids and their surrounding filaments and clusters represent the web-like architecture of the universe, a phenomenon that reflects the influence of gravity over billions of years. Gaps are crucial to understanding cosmological evolution because they help scientists investigate the origin and nature of cosmic structure. By studying the vacuum, researchers can understand the changes in density that occurred in the early universe. Moreover, the properties of cosmic voids challenge our understanding of dark energy, the mysterious force that causes the universe to accelerate. The behavior of matter in and around voids can reveal valuable information about how dark energy affects the expansion of space. For example, observing how galaxies move in and around voids can provide information about the distribution of mass in the universe and help us understand cosmic dynamics. The study of cosmic voids also raises interesting questions about the fundamental nature of the universe. They serve as testing grounds for cosmological models, allowing researchers to assess the validity of theories such as the Standard Model of cosmology. As science advances and observational techniques improve, space probes continue to unravel the mysteries of the universe, enhancing our understanding of the governorship of cosmic evolution. Dark matter plays an important role in the formation and evolution of cosmic structures throughout the universe. Although invisible, neither emitting nor absorbing light, dark matter makes up about 27% of the total mass-energy content of the universe. Its gravitational influence is key to understanding how galaxies, clusters, and even larger structures such as superclusters and cosmic filaments are formed and maintained. In the early universe, after the Big Bang, matter began to clump together under the force of gravity. Although the normal matter that emits light and forms stars and galaxies begins to accumulate, it is dark matter that does not appear to form the basis of this cluster. Dark matter does not interact electromagnetically, meaning it does not collide with matter to dissipate energy. This property allows it to remain gravitationally bound and form massive halos surrounding galaxies and clusters. These halos act as gravitational wells, attracting ordinary matter and helping the formation of stars, galaxies, and larger structures. The processes of cosmic evolution and structure formation are closely related to the behavior of dark matter. When galaxies merge or interact, their dark matter can also collide and merge, which can lead to the growth of large galaxies and galaxy clusters. Understanding the dynamics of dark matter interactions helps scientists explain phenomena such as the rotation curves of galaxies. These curves show that stars orbiting outside galaxies are moving faster than expected based on visible matter. This suggests that there is additional invisible mass associated with dark matter. Astronomical observations and simulations of large-scale structures shed more light on the role of dark matter. By mapping the distribution of galaxies and clusters, researchers can map the corresponding distribution of dark matter. Projects such as gravitational lensing provide direct evidence of the existence and distribution of dark matter throughout the universe by measuring how light from distant objects is bent by massive structures. As researchers continue to explore the nature of dark matter, they enhance our understanding of its profound effects on the cosmic landscape and the structure of our universe. Beyond our observable universe lies a tantalizing and enigmatic realm. Although we can analyze the structures in the cosmic environment, understanding the nature of these cosmic structures is influenced by many different cosmological theories. One common idea is that the conditions surrounding these structures may vary, resulting in different formations. For example, while our universe exhibits a specific distribution of galaxies, clusters, and voids, other regions may vary in density and order, resulting in different large-scale structures. One hypothesis suggests that physical laws may differ in different regions of the universe. If fundamental constants such as gravity or the speed of light differ from our observable horizon, the evolution of cosmic structures in these regions may produce results that differ dramatically from what we witness nearby. Such changes could lead to exotic astrophysical entities or entirely new celestial shapes that defy our current understanding of physics. In addition to potential changes in physical laws, the overall geometry of spacetime is a critical factor influencing the structure of the universe. Measurements of the cosmic microwave background radiation suggest that the observable universe appears to be flat. However, if the universe is truly infinite and far beyond what we can observe, it could introduce various curvature features that could affect the development of large-scale cosmic structures. The concept of the multiverse also comes into play, where our universe is potentially one of countless others, each with its own unique physical properties and structural formation processes. In such a scenario, some universes may adopt strange structures or even strange rules governing their cosmic evolution. While these ideas remain speculative, they drive the imaginations of scientists and theorists, furthering the exploration of the mysteries of the universe. Attempting to understand these hypothetical cosmic realms beyond the visible universe deepens our uncertainty. Dark matter is a mysterious, non-luminous component of the universe that does not emit, absorb, or reflect light, making it invisible to conventional observational techniques. Dark matter is thought to make up about 27% of the mass energy of the universe. Scientists estimate its existence based on its effects on visible matter, radiation, and the overall structure of the universe. One of the strongest lines of evidence for dark matter comes from observations of galaxy rotation curves. When astronomers measure the speed of stars orbiting in the outer regions of galaxies, these stars move much faster than expected based on the gravitational effects of visible matter such as stars and gas. According to Newtonian physics, they should show a decreasing velocity as they move away from the galactic center. However, the observed velocity remains constant, indicating that the galactic halo contains more mass than can be accounted for by stars and gas alone, possibly in the form of dark matter. Another important piece of evidence comes from gravitational lensing, the phenomenon in which light from distant galaxies is bent by the gravitational pull of large foregrounds such as galaxy clusters. Observations show that the amount of bending goes beyond that which depends only on the apparent mass. This inconsistency suggests that there is additional invisible mass that exhibits gravitational pull, consistent with the presence of dark matter. Moreover, the distribution of galaxies in the universe follows a web structure under the influence of dark matter. Cosmic structure formation simulations involving dark matter agree closely with observations of the large-scale structure of the universe, such as galaxy clusters and voids. These models suggest that dark matter acts as clusters of visible matter that guide the formation of galaxies and other cosmic structures. The exact nature of dark matter remains a deep mystery, and various candidates have been proposed, such as non-massive particles. Research is ongoing, using cutting-edge technologies and experiments aimed at directly or indirectly detecting dark matter. The search for dark matter is important because it not only holds the key to understanding the composition of the universe, but also informs the fundamental laws that govern the cosmos. Dark matter has a profound effect on galaxy formation and the overall architecture of the universe. Its gravitational properties are important in shaping the large-scale structure we observe in the universe today. In the early universe, shortly after the Big Bang, dark matter began to clump together, forming massive halos that provided a gravitational field within which ordinary matter could gather. This high concentration of dark matter created gravity wells that attracted gas, dust, and other simple matter, facilitating the birth of galaxies. As galaxies form, their dark matter plays an important role in determining their size, mass, and rotation speed. Dark matter helps maintain the stability of galaxies by providing additional gravitational pull only with visible matter. This stability is particularly important because the forces at play during galaxy formation are enormous, and the gravitational pull of dark matter allows complex structures to form that do not collapse under their own dynamics. When galaxies interact or merge, the dynamics of their dark matter has a significant impact on the outcome of these events. For example, during a merger between two galaxies, their dark matter halos can collide and merge with visible matter. This interaction can lead to the formation of larger galaxies, which often exhibit different properties compared to smaller ones. This merger process is a critical aspect of galaxy evolution, contributing to the development of cosmic structures throughout the universe. On a larger scale, dark matter represents the overall distribution and motion of galaxies. The gravitational influence of dark matter creates the structure of the cosmic web, where galaxies and clusters form along filaments and nodes with large gaps between them. This gravitational network shows how dark matter organizes space and affects the motion of galaxies over time, shaping the dynamic behavior of galaxies and clusters as they move through the evolving universe. Dark matter is more than just a facilitator of cosmic evolution. It serves as the primary force driving the formation and construction of galaxies and the larger cosmos. The search for dark matter particles has led scientists to propose several interesting candidates, each from a different theoretical background in particle physics and cosmology. One of the most widely studied candidates is the weakly interacting massive particle, often abbreviated as WIMP. WIMPs are predicted to have masses on the order of hundreds of GeV or giga-electron volts and interact with the weak nuclear force and gravity. The theory postulates that they were produced in large quantities in the early moments after the Big Bang. Direct detection of WIMPs will be difficult due to their weak interactions, but some experiments aim to observe scattering events with potential matter. Another promising category of dark matter candidates is the hypothetical elementary particle proposed to solve problems related to quantum chromodynamics. Particles are light, slow-moving particles that can make up a large portion of dark matter. They will interact very weakly with other particles, effectively repelling them. Researchers are exploring the potential for detecting axons through experiments that look for them to convert into photons when exposed to strong magnetic fields. There are also supersymmetric particles, which arise from theories that extend the standard model of particle physics. In these models, each elementary particle has different properties. Candidates from supersymmetry, such as neutralinos, have the necessary properties to account for dark matter. Their stability and interactions governed by the weak force make them strong candidates in some theoretical frameworks. Finally, supermassive black holes provide an alternative explanation for dark matter. These would arise from changes in density in the larger universe, potentially accounting for the effects of dark matter through gravitational interactions. Although this theory differs from ordinary particle candidates, it remains a point of active research given the complexity of cosmological evolution. These candidates bring together the various approaches taken to solve the dark matter enigma. Ongoing experiments are designed to detect or rule out these possibilities, improving our understanding not only of dark matter, but of the fundamental physics of the universe. Each approach promises to advance scientific knowledge and may lead to profound discoveries about the composition of the universe and the laws that govern it. Dark energy is an enigmatic form of energy that permeates all of space and is responsible for the observed acceleration of the universe. Dark energy, which accounts for about 73% of the total mass energy content of the universe, has puzzled scientists since its discovery. Unlike ordinary matter and dark matter, which are gravitationally attracted, dark energy exerts a repulsive force, causing galaxies to accelerate apart from each other. Traces of dark energy were first discovered in the late 20th century, primarily through observations of distant supernovae. In the mid-1990s, two independent research teams, the Supernova Cosmology Project and the High-Z Supernova Search Team, set out to measure the luminosity of JA supernovae, which serve as a reliable standard candle for determining cosmic distances. By observing these supernovae, teams would discover that the universe's expansion is slowing due to gravity. However, their data showed a surprising result. The supernova appeared darker than expected, indicating that they were farther away than previously thought. This led researchers to conclude that the expansion of the universe is accelerating rather than slowing down. The key to understanding this acceleration lies in the concept of dark energy. To explain the observations, scientists introduced dark energy as the driving force behind the accelerated expansion. Various theoretical frameworks have been proposed to describe dark energy, one of the most famous models of the cosmological constant. The cosmological constant, proposed by Albert Einstein at the beginning of the 20th century, simultaneously complements the energy density. This reflects the idea that as the universe expands, the energy density remains constant. Other theories have emerged, including quintessence, which suggests that the density of dark energy may change over time. Despite these various models, the true nature of dark energy remains elusive. Observations of the cosmic microwave background, the large-scale structure of the universe, and other astrophysical phenomena have helped improve our understanding of dark energy. Ongoing research continues to investigate this mysterious substance, as unraveling its nature could shed light on fundamental aspects of the universe and the ultimate fate of cosmic evolution. Dark energy plays an important role in the future of the universe, primarily because of its role in the accelerated expansion observed over the past few billion years. As dark energy continues to exert its influence, it shapes potential scenarios for the ultimate fate of the universe. The exact nature of dark energy remains an open question, but its consistency suggests several futures for the universe. Big Freeze Scenario. In this model, as the universe expands at a rate controlled by dark energy, galaxies gradually fade away from our observable horizon. Over large timescales, star formation will slow down, leading to an increasingly cold and dark growing universe. Existing stars will run out of nuclear fuel, and without new stars forming, most of the matter will remain in the form of black holes and white dwarfs. Eventually, the universe will reach a state of thermodynamic equilibrium, characterized by a uniform temperature near absolute zero, rendering it a desert and inert space. Another scenario is a Big Rip, where the influence of dark energy increases, causing the escape to expand. In this model, the accelerated expansion can be so pronounced that it eventually separates galaxies, stars, and even atoms. If the energy density of dark energy increases without limit, all large-scale structures will collapse, ultimately leading to a catastrophic end to the universe. At the other end of the spectrum, some theories suggest that dark energy could evolve over time, perhaps leading to a steady state or even transitioning to gravitational forces. This change could reverse the current acceleration of cosmic expansion, allowing galaxies to merge and form larger structures, leading to a cyclical pattern of cosmic evolution. As researchers gather more information from observations of supernovae, the cosmic microwave background radiation, and galactic scattering, they aim to improve our understanding of dark energy and its effects on the universe. Each of these potential destinies points to the complex relationship between dark energy and the cosmos, revealing how this mysterious force can ultimately shape evolution and the fate of everything within it. The evidence for the expansion of the universe is strong and multifaceted, contributing to our understanding of cosmological dynamics. One of the earliest and most compelling evidences comes from observations of galaxies and their redshifts, recognized by Edwin Hubble in the late 1920s. Hubble noted that distant galaxies are moving away from us, and the light they emit shows a shift to the red end of the spectrum. This red shift indicates that the wavelengths of light are stretched as galaxies shrink, a phenomenon consistent with the Doppler effect. Hubble formulated his law, which states that the farther away a galaxy is, the faster it is moving away and the universe is expanding. In addition, the cosmic microwave background rays, the glow left over from the Big Bang, provide further support for this expansion. Discovered in the 1960s, this relic radiation is remarkably uniform, but there are small variations that reveal information about the density and temperature of the universe. Measurements from satellites, such as the Wilkinson Microwave Anisotropic Probe and the Planck mission, show these changes with great precision. According to the data, the universe has been expanding since its creation, and the cosmic microwave background serves as a snapshot of the universe as it was around 300,000 years ago, after it cooled enough to form atoms. Supernovae also contribute to the evidence for the universal expansion, particularly type Ia supernovae, which serve as reliable standard candles for measuring astronomical distances. Observations at the end of the 20th century showed that these supernovae were less luminous than expected, suggesting that they were far away due to the acceleration of the universe's expansion. This discovery was instrumental in proving not only the expansion of the universe, but the expansion rate is increasing due to dark energy. Finally, the large-scale structure of the universe, including the distribution of galaxies and cosmic filaments, provides additional evidence for expansion. Current observations show that galaxies are not uniformly distributed. Instead, they form a large cosmic web structure that interacts with gravity. This distribution is a direct result of the expansion history of the universe, further reinforcing the paradigm of a dynamically evolving cosmos under the influence of forces at play since the Big Bang. Together, this evidence creates a powerful picture of an ever-expanding universe, with each piece contributing to our understanding of its origins and evolution over time. The Hubble constant is a key parameter that describes the rate at which the universe is expanding. It shows the relationship between a galaxy's distance and its rate of recession, providing a measure of how quickly galaxies are moving away from us as the universe expands. The Hubble constant is usually expressed in megaparsecs per kilometer per second, meaning that for every additional megaparsec, the galaxy is receding by a certain number per second. Edwin Hubble's discovery of this relationship in the late 1920s fundamentally changed our understanding of the universe. His observations showed that galaxies farther from Earth are receding at a greater rate, indicating that the universe itself is expanding in one direction. This expansion can be thought of as the stretching of space, with the galaxies embedded in that space dissipating over time. Understanding the Hubble constant is critical to determining the size and age of the universe. By measuring the recession velocities of different galaxies and their distances using methods such as standard candlestick or redshift measurements, astronomers can calculate the Hubble constant. This measurement allows scientists to estimate how long the universe has been expanding since the Big Bang, yielding its age, which is currently about 13.8 billion years. However, it should be noted that measurements of the Hubble constant yielded slightly different values depending on the methods used. Planck satellite observations measuring the cosmic microwave background radiation suggest a certain value for the Hubble constant, while measurements from large surveys of supernovae and galaxy distributions provide larger values. This discrepancy has led to debate and research in the field of cosmology, as scientists seek to reconcile these differences and better understand the underlying physics of the universe's expansion. Ultimately, Hubble serves as an important bridge connecting observations of constant recession velocities and distances, strengthening its role in understanding the expanding universe and guiding future investigations into its fate. Cosmic acceleration refers to the observed expansion of the universe over the past few billion years. This continuum behavior indicates that the galaxies are moving away from each other at increasing speeds rather than slowing down, as would be expected from gravitational acceleration. The discovery of cosmic acceleration changed our understanding of the dynamics of the universe and had important implications for cosmology. The main explanation for cosmic acceleration is dark energy, a mysterious form of energy that permeates space and resists gravity. Dark energy is thought to make up 73% of the total energy density of the universe. Unlike ordinary matter, which has a gravitational pull, dark energy appears to be a repulsive effect pulling galaxies apart. The nature of dark energy remains one of the most profound enigmas of modern astrophysics, with various theories proposed to describe its properties, including the cosmological constant, which is a constant energy density. Observations supporting cosmic acceleration come primarily from studies of distant supernovae, particularly type Ia supernovae. These supernovae serve as reliable distance indicators, allowing astronomers to measure the expansion history of the universe. When the researchers found that these supernovae were weaker than expected, it showed that they were farther away than previously thought, leading to the conclusion that the expansion of the universe is accelerating rather than accelerating. Another piece of evidence for cosmic acceleration is observations of the cosmic microwave background radiation and large-scale structure. Measurements of changes in the cosmic microwave background after the Big Bang provide insight into the density and composition of the early universe. The subsequent spread of galaxies and galaxy clusters through space is consistent with an accelerated expansion scenario, as structures formed from density fluctuations are influenced by dark energy. Despite extensive research on dark energy and cosmic acceleration, questions remain about its true nature and behavior. Ongoing experiments and observational campaigns aim to improve our understanding, potentially revealing physics and changing our understanding of the evolution and fate of the universe. The implications of cosmic acceleration and dark energy are not only interesting, but also delve into deeper questions about the very fabric of reality. The expansion of the universe is of great importance not only for the regions we can observe, but also for the regions beyond the observable limits. As the universe expands, it affects the dynamics and distribution of matter on large scales, and this expansion drives the evolution of cosmic structures both within our observable universe and in regions beyond it. One of the main effects of this expansion is the notion that the regions beyond our observable universe may be shrinking away from us at speeds exceeding the speed of light due to the metric expansion of space. This means that light from galaxies in these distant regions can never reach us, remaining forever beyond our cosmic horizon. As the universe continues to expand, many of these regions will move away from our observables, leading into the future, when the night sky will slowly empty of distant galaxies. This eventual isolation can lead to a universe that appears dark and desolate, changing our perception of space over cosmological timescales. Magnification effects raise interesting questions about the potential existence of structures beyond our observable universe. While we cannot directly observe these regions, theoretical models suggest that they may contain galaxies, clusters, and cosmic filaments similar to our observable limits. However, these structures evolve differently depending on local conditions, gravitational interactions, and dark energy distribution. Such changes may mean that the universe we see is not just an extension of what we can observe, but may offer unique features. In addition, the rate of expansion can affect the fate of the universe. If the properties of the dark model change, as some models suggest, this could lead to very different cosmic scenarios in the observable and unobservable regions of the universe. For example, if dark energy becomes stronger, it could lead to Big Rip-like scenarios where cosmic structures are disrupted, even affecting the integrity of the farthest reaches of space. Ultimately, as scientists continue to study the fundamental laws governing the expansion of the universe, our understanding of its consequences will be near and far. Uncharted regions of the universe may hold secrets that defy our understanding and help us understand the fabric of reality, even if we never see it with our own eyes. The ultimate fate of the universe is a topic of great intrigue among cosmologists, with prevailing theories suggesting several potential scenarios based on the expansion of the universe and the nature of dark energy. As the universe continues to expand, it will push galaxies further apart. This expansion, driven by dark energy, is accelerating over time, leading to the possibility of a superfreeze. In this scenario, the universe becomes increasingly cold and desolate. Stars run out of fuel and galaxies recede until they fall into obscurity. Alternatively, some models predict a major collision. In this scenario, if the universe is dense enough, gravity can eventually stop expanding. The universe would then collapse back under its own gravity, potentially creating a singular state similar to the conditions at the beginning of the universe. This collapse could return all matter to an infinitely dense point, possibly leading to another Big Bang and the birth of a new universe. Another interesting possibility is the Great Rip. This theory suggests that if dark energy becomes stronger, it can tear apart galaxies, stars, planets, and even atoms. In this case, the fabric of the universe would eventually rupture, causing all structures to collapse violently. Finally, there is the concept of a steady-state universe, in which the expansion continues indefinitely, but the universe does not change over time, filled with new matter continuously created to fill the voids left by the expanding universe. These theories highlight the complexity and uncertainty surrounding the fate of our universe, calling for further exploration and research in the field of cosmology